Hello there, and welcome to the Sleepy Science Channel. This evening, our journey turns inward into the hidden landscape within your own skull, the human brain. It is smaller than a melon, soft as custard, and yet somehow it contains your memories, your imagination, and the shimmering thread of your identity. Scientists have found that the brain can predict the future before events unfold, that it sometimes invents entire stories to fill in the gaps of memory, and that a single thought leaves a physical trace behind. Inside its folds are networks so vast, they rival the stars in our galaxy. It is at once familiar and astonishing, a universe folded into 3 pounds of tissue. If you enjoy these gentle journeys, consider liking and subscribing, or share a thought in the comments. It helps others find their way here too, one sleepy soul at a time. But for now, you don't need to do anything at all. Just settle in, let your shoulders soften, and let your breathing fall into a slower rhythm. Now, if you're ready, let's begin. The brain predicts the future a few seconds ahead of reality. Your brain is not just a passive receiver of the present moment, it is a prediction machine. Every fraction of a second, your brain builds a model of what it expects will happen next, anticipating sounds, movements, and even the words you're about to hear. In fact, brain scans show that activity often rises in anticipation of an event before the senses actually register it. This predictive coding helps you catch a ball, understand speech even in noisy rooms, or step out of the way of danger almost instantly. Without this ability, life would feel disjointed, as if reality were arriving in jagged frames. Instead, your brain smooths out the world, always leaning a heartbeat into the future, ensuring that your experience feels seamless, continuous, and alive. Scientists have reconstructed images directly from brain signals. One of the most astonishing frontiers of neuroscience is the ability to peer into the mind and reconstruct its contents. Using functional MRI scans and artificial intelligence, researchers have successfully rebuilt rough images of what people are looking at, shapes, faces, even simple movie clips, using nothing but patterns of teen brain activity. While the results are blurry, they capture enough detail to be recognizable, suggesting that thoughts and perceptions leave measurable fingerprints in neural activity. This technology opens both exciting and unsettling possibilities. Perhaps one day, we may be able to record dreams, visualize memories, or even share inner experiences in ways that today feel like science fiction. For now, these experiments reveal something breathtaking, that the private theater of the mind, long hidden from the outside world, can be glimpsed through the shimmering electrical language of the brain. Your brain can trick you into seeing things that aren't there. Perception is not simply a mirror of reality. Sometimes, your brain invents details, colors, or patterns that don't exist in the world around you. Classic optical illusions are a gentle demonstration of this, showing how lines can look longer, colors can seem brighter, or shapes can appear to move when nothing is happening. But the effect runs deeper. In moments of sensory deprivation, stress, or illness, the brain can generate full-fledged hallucinations, sounds, sights, even entire scenes that feel real. This happens because your brain is always trying to interpret incomplete information, filling in gaps with its best guess. Most of the time, this makes perception smooth and useful. Occasionally, however, it overshoots, creating a phantom where none exists. It is a humbling reminder that what we call reality is always filtered and reconstructed inside the theater of the mind. People with split brains sometimes act as if two minds share one body. In rare medical cases where the connection between the two hemispheres of the brain, the corpus callosum, is severed, something astonishing can happen. Each hemisphere begins to act with a degree of independence, as if two consciousnesses are sharing the same body. One hand may reach for a shirt while the other hand pushes it away. A person may verbally deny seeing an object presented to one eye, while their other hand nonetheless points directly to it. These split brain studies reveal that the left and right hemispheres specialize in different functions, and that our sense of a unified self is a delicate construction. Beneath the seamless unity we feel, the brain is actually a federation of processes. Sever the links between them, and the hidden multiplicity of the mind emerges, showing us how fragile the illusion of singular identity really is. The brain sometimes creates entirely fake stories to explain gaps. Your brain hates uncertainty. When something doesn't make sense, it will often invent an explanation, and you may believe it without question. This phenomenon, known as confabulation, happens when the brain fills memory gaps or explains actions in ways that feel coherent but are actually false. For example, patients with certain brain injuries might insist they've eaten breakfast when they haven't, or confidently explain why they chose an object even though the real reason was hidden from their awareness. Confabulation isn't lying. It's the brain's way of preserving a continuous narrative of self. And it doesn't only occur in cases of brain damage. Everyday memory works the same way, smoothing over errors and stitching fragments into seamless stories. Much of what you think of as memory is not a perfect record, but a careful fiction crafted by the mind. Some people can remember every day of their lives in detail. For most of us, memory is selective and hazy, with yesterday blending into the week before. But a handful of people possess an extraordinary gift, highly superior autobiographical memory, or HSAM. These individuals can recall the weather, conversations, and even what they ate on any given day of their lives, stretching back decades. Ask them about a random date, and they can tell you the day of the week, what news was happening, and what they were wearing. Brain scans suggest that their memory networks are unusually active and densely connected, though scientists still don't fully understand why. Interestingly, this gift can feel like a burden. The inability to forget means reliving painful experiences as vividly as joyful ones. Their minds act like living archives, preserving a detailed, ceaseless timeline of existence, a reminder of how astonishingly variable human memory can be. The brain generates enough electricity to light a small bulb. Though your brain runs on chemistry and biology, it is also an electrical powerhouse. At any given moment, billions of neurons are firing, sending signals across tiny gaps using quick jolts of electricity. The combined voltage of this buzzing network is enough to light a small LED bulb, around 20 watts. It's a humbling comparison. Inside your skull, thoughts, memories, and emotions all depend on faint currents flickering across tissue softer than tofu. The brain's electrical nature also makes it readable by machines. Technologies like EEG capture the faint rhythms of brain waves, turning invisible activity into measurable patterns. These patterns reveal when you are awake, dreaming, or deeply asleep. The idea that the seat of your mind, the place where you live, is also a living electrical field, glowing faintly with energy, is both haunting and beautiful. Your brain is more active at night than during the day. You might think that sleep is a time when the brain powers down, but the opposite is true. In many stages of sleep, particularly during rapid eye movement REM, the brain is buzzing with activity, in some regions, even more than when you are awake. Neurons fire in patterns that consolidate memories, process emotions, and weave together the strange imagery we call dreams. This hidden activity is why you often wake with solutions to problems, flashes of creativity, or a lighter emotional burden. While the body rests, the brain runs its nightly workshop, sorting, repairing, and reshaping the mind. To outside observers, you appear still, even unconscious, but inside your head, a universe of activity unfolds, carrying you across the landscapes of memory and imagination. In its busiest hours, the sleeping brain is quietly hard at work, reinventing you for the morning to come. Blind brains can repurpose the visual cortex for touch and sound. When someone is blind, especially from birth, the brain does not let the unused visual cortex lie dormant. Instead, it recruits that vast territory of neurons for other senses, amplifying touch, sound, and even smell. This rewiring explains why blind individuals often develop extraordinary abilities, such as reading Braille with incredible speed or identifying subtle sounds that sighted people would miss. Brain scans show that their visual cortex lights up when their fingers trace patterns or when they navigate by sound. This remarkable adaptability, called neuroplasticity, reveals that the brain is not rigidly hardwired but astonishingly flexible, ready to reorganize itself depending on the body's needs. It suggests that hidden within every brain is untapped potential, waiting to be awakened if circumstances demand. The brain is not a fixed map, but a living, evolving landscape, capable of rewriting itself. People who lose one sense often develop superhuman abilities in another. When one doorway to the world closes, others can grow wide open. People who lose hearing may develop heightened vision, detecting flickers of movement with uncanny sensitivity. Those who lose sight may notice faint textures or sounds with astonishing precision. This phenomenon is not just poetic but measurable. The brain reallocates its resources, expanding the regions devoted to the remaining senses. In some cases, the abilities seem almost superhuman, like identifying people by footsteps alone or navigating spaces using subtle echoes. These adaptations show that the brain is always searching for balance, recalibrating itself to maximize survival and perception. It reminds us that human potential is deeply elastic. Hidden capabilities lie dormant, waiting for the brain's remarkable flexibility to bring them forth. In every mind lives a silent promise, the power to change, adapt, and evolve in ways that defy expectation. Some people see sounds or hear colors through synesthesia. For most of us, senses remain separate. We hear music, see colors, taste food. But for people with synesthesia, the boundaries blur. A sound might be tinged with color, letters might appear shaded with hues, or numbers might carry textures and personalities. To them, the world is enriched with cross-sensory overlays that feel entirely natural. Scientists believe this happens when neural pathways between sensory regions are unusually connected, allowing signals to blend. Some synesthetes report tasting shapes or feeling the texture of sounds. This rare phenomenon is not just a curiosity. It can boost memory and creativity, since stimuli become multi-layered and unforgettable. Famous artists, composers, and writers have described experiencing it, hinting that synesthesia may have fueled some of humanity's most brilliant expressions. It is a reminder that perception is not fixed but deeply individual. Each brain paints its own version of reality. The brain can adapt to seeing the world upside down. Imagine wearing special goggles that flip the world completely upside down. At first, everything feels impossible. Walking, reaching, even pouring water. But after days or weeks, the brain begins to adapt. Astonishingly, it can rewire perception so thoroughly that the inverted world feels normal. When the goggles are removed, the adjustment flips again, and ordinary vision can feel bizarrely reversed until the brain recalibrates. This experiment, performed in various forms for over a century, demonstrates the brain's profound plasticity, its ability to remap sensory input to fit reality. It means that perception isn't simply about the eyes, it's about how the brain interprets and organizes the information. Reality is flexible, stitched together in whatever way the mind can make sense of it. The fact that the world can literally turn upside down and then feel right again is proof of just how adaptable the brain truly is. The brain creates a constant stream of predictions about what happens next. Your brain is not just reacting, it is constantly guessing. Every sound, every movement, every glance is met with predictions about what should come next. When someone speaks, your brain anticipates the end of their sentence before the words arrive. When you walk through a familiar room in the dark, your mind sketches out where objects should be. This predictive coding smooths reality, allowing you to navigate without feeling constant surprise. Sometimes the predictions misfire, as in optical illusions, where expectation overrides truth. But most of the time, they save you milliseconds, and those fractions of a second can mean survival. The brain's ceaseless forecasting makes experience feel continuous, as if reality flows rather than lurches. In a way, you are always living slightly ahead of the moment, your mind leaning into what has not yet come, blurring present and future into a seamless stream. People can have out-of-body experiences triggered by brain stimulation. Some people describe the eerie sensation of floating above their body, watching themselves from outside. Mystics have written about it for centuries, but neuroscience has discovered that the sensation can sometimes be induced artificially. Electrical stimulation of the temporoparietal junction, a region that helps integrate vision, balance, and body awareness, can cause patients to feel as if they are leaving their body, even when they are lying still. This suggests that our sense of being inside ourselves is a construction of the brain, woven from sensory inputs. When those signals misalign, the self can feel displaced. While such experiences remain deeply mysterious and often profound, they point to a simple truth. Even the most intimate feeling of being you is carefully generated by the brain, and it can shift, unravel, transform under the right conditions. Identity itself is a fragile illusion of neural balance. Electrical brain stimulation can make people laugh against their will. During neurosurgery, doctors sometimes apply tiny electrical currents to brain tissue to map its functions. In rare cases, when certain regions are stimulated, patients suddenly burst into uncontrollable laughter. They are aware of the strangeness but cannot stop, often describing the moment as inexplicably funny, even if nothing humorous is happening. Similarly, other stimulations can bring tears, fear, or a flood of memories. These discoveries show how emotions, which feel so personal and profound, can be switched on like lights when the right circuits are triggered. It doesn't make emotions any less real, but it reveals that joy, sorrow, or awe are rooted in precise biological machinery. The idea that laughter, that purest expression of delight, can be summoned by a gentle zap of electricity is at once unsettling and wondrous, blurring the line between the mechanical and the deeply human. Another brain lesion made a man believe his parents were imposters. In a strange neurological condition known as Capgras delusion, patients recognize the faces of loved ones, but insist they are imposters. One man, after a brain injury, looked at his parents and believed they had been replaced by convincing doubles. Scientists think this happens because the visual recognition pathway to the emotional centers of the brain is disrupted. The face is seen and identified, but it fails to trigger the familiar warmth of emotional response. The mismatch convinces the mind that something sinister has occurred. Cases like this reveal how fragile the links are between recognition, memory, and feeling. To the person affected, the delusion is utterly real, a terrifying fracture in the fabric of trust. It shows that our sense of reality, and even the bonds of family, depend on the seamless cooperation of circuits hidden deep within the brain. Damage to a single brain area once made a man unable to feel fear. In one extraordinary case, a woman with damage to her amygdala, the almond-shaped structure central to processing fear, became nearly fearless. She could handle snakes and spiders, wander dark alleys alone, and watch horror movies without flinching. While this might sound liberating, fear is a survival tool, guiding us away from danger. Without it, she was more vulnerable to real threats. The case gave neuroscientists profound insight into how emotions are localized and how specific brain regions sculpt our inner lives. Fear, often experienced as a vague sense of dread, is in fact anchored in physical structures. When those structures are compromised, the emotion can vanish. It demonstrates both the power and the fragility of our biology, that something as primal and universal as fear can be erased by the smallest lesion in the brain's intricate circuitry. The brain can react to danger before you're even aware of it. Imagine stepping off a curb and jerking back as a car rushes by, only later realizing what happened. This speed comes from pathways in the brain that bypass conscious thought. Visual information can travel directly to the amygdala, triggering a cascade of fight-or-flight responses before you have time to think. Your heart races, your muscles tense, and you leap to safety in under half a second. Conscious awareness catches up only afterward, stitching a story around the reflex. These hidden circuits prove that survival depends on reaction times far faster than deliberate thought allows. It also shows that your experience of life is always slightly delayed, with unconscious processes guiding you first. In this way, the brain is both protector and storyteller, acting in your defense, then filling in the narrative so that it feels like you are fully in control. Einstein's brain had unusual folds and connections. After Albert Einstein's death, his brain was preserved and studied, revealing unusual features. The parietal lobes, linked to spatial reasoning and mathematics, were notably enlarged, and certain regions showed unique folds and patterns unseen in most people. His corpus callosum, the bridge connecting the two hemispheres, appeared thicker, suggesting enhanced communication between different brain areas. While no single feature explains his genius, the differences hint at a biological foundation for his extraordinary imagination. Yet Einstein himself emphasized curiosity, persistence, and playfulness as the true engines of discovery. His brain reminds us that structure matters, but the mind's brilliance also grows from habits of thought, wonder, and relentless exploration. It is a blend of nature and nurture, the physical canvas of the brain shaped by the creative strokes of a lifetime of inquiry and dreaming. London taxi drivers grow larger brain regions for navigation. To qualify as a London taxi driver, one must memorize the knowledge, thousands of streets and landmarks across the city. Brain scans have shown that these drivers develop enlarged hippocampi, the brain's navigation centers. The more years spent navigating, the larger this region becomes, a clear demonstration that experience reshapes anatomy. This discovery was one of the first to show neuroplasticity in adults at such a striking scale. It means the brain isn't fixed after childhood, but continues to mold itself in response to challenge and practice. Whether learning music, language, or maps of a city, the brain lays down new structures to meet new demands. For the drivers, this adaptation becomes a living atlas, etched into neural tissue. Their minds carry a miniature London within them, a testament to the way effort sculpts the very architecture of the brain. Music can reshape the brain more than almost any other activity. When you play an instrument, your brain engages nearly every major region at once. Motor areas control your fingers, auditory regions process the sounds, and emotional centers respond to melody and harmony. Over time, this full brain workout leaves a physical imprint. Studies show that musicians often have larger corpus callosums, the bundle of fibers connecting both hemispheres, allowing for faster communication across the brain. Regions involved in hearing, memory, and motor coordination also grow denser and more active. Even simply listening to music can strengthen neural connections, enhancing mood regulation and memory. It is no wonder that music therapy is used to support stroke recovery and emotional healing. Music is not just entertainment, it is a form of structured sound that sculpts the brain, rewiring circuits and leaving behind echoes of rhythm and harmony woven into the very architecture of the mind. Creativity lights up different circuits than logical thinking. Logic and creativity often feel like opposites, yet both rely on the brain's remarkable networks. When you solve a math problem, the brain's executive and analytical circuits take charge, emphasizing order and precision. But when you paint, write, or improvise, entirely different circuits spark to life, especially in the default mode network and associative areas that link distant concepts. Brain scans show that creative thought involves unusual patterns of connectivity, a kind of neural jazz session where unexpected regions play together. Interestingly, the most creative moments often occur when analytical areas quiet down, allowing looser, freer associations. This balance explains why creativity often blossoms when you're relaxed, daydreaming, or just before sleep. The brain's ability to switch modes, from razor-sharp analysis to open-ended invention, is what makes human thought both practical and profoundly imaginative, capable of engineering rockets and composing Ga. Symphonies with the same neural canvas. Eureka. Moments come from unusual synchronization of brainwaves. The sudden flash of insight, the aha or eureka moment, feels like magic. But neuroscience shows it arises from a shift in brainwave patterns. Just before a breakthrough, the brain often enters a burst of gamma activity, a rhythm associated with hill-level integration across distant regions. These waves allow connections to form between ideas that previously seemed unrelated. It's as if the brain suddenly harmonizes, producing clarity from chaos. Such moments are unpredictable, but can be encouraged by relaxation, play, or stepping away from the problem. That's why solutions often appear in the shower, on a walk, or in a dream. The insight feels sudden, but in reality, your brain has been working beneath awareness, quietly assembling the puzzle. When the synchronization finally locks into place, the solution surges into consciousness, a neural spark that feels like a gift from nowhere. Your brain builds entirely new pathways when you learn something. Every time you learn a skill, memorize a fact, or practice a movement, your brain changes. Neurons reach out to form new synapses, strengthening the pathways that support the behavior. Over time, repeated use makes these circuits more efficient, as if the brain is laying down a well-worn trail through a forest. This physical remodeling is called neuroplasticity, and it underlies all growth and learning. Remarkably, even simple repetition, like practicing scales on a piano or rehearsing vocabulary, leaves behind new structures in the brain. These pathways can expand or shrink depending on use. Use it or lose it is literally true for neural circuits. The process never stops, continuing into old age, though more gradually. Each lesson you absorb rewires you, leaving permanent traces in the architecture of your mind, shaping who you are and who you are still becoming. Stress can physically shrink parts of the brain, while short bursts of stress can sharpen focus and prepare the body for action. Chronic stress takes a toll on the brain. Prolonged exposure to stress hormones like cortisol can shrink the hippocampus, a region critical for memory and learning. It can also weaken connections in the prefrontal cortex, impairing decision-making and emotional regulation. At the same time, stress may enlarge the amygdala, intensifying fear and anxiety responses. This rewiring creates a cycle in which stress makes the brain more vulnerable to further stress. The good news is that the brain is resilient. Practices like mindfulness, exercise, and social connection can reverse some of these changes, restoring balance. Stress literally reshapes the mind, but so does recovery. It is a powerful reminder that mental states are not abstract clouds hovering above the brain, but biological forces carving pathways into its very structure. Meditation can thicken the brain regions linked to calm and focus. Meditation may feel like simply sitting quietly, but inside the brain, profound changes unfold. Brain scans show that regular meditation can increase the thickness of the prefrontal cortex, improving attention and emotional regulation. It also enhances connectivity in networks related to empathy and compassion, while reducing activity in the amygdala, softening stress and reactivity. Long-term practitioners often show structural growth in gray matter density, particularly in regions tied to self-awareness and perspective-taking. These changes occur even in beginners after just weeks of practice, proving that the benefits are not limited to lifetimes of devotion. In a world of noise and constant stimulation, meditation offers a way to literally reshape the brain toward calm. The quiet repetition of breath and awareness is enough to sculpt new circuits, showing that peace of mind is not just a feeling, but a skill your brain can grow. Extreme meditation masters can control their body temperature with thought. In the high Himalayas, monks practicing advanced meditation techniques have been observed drying wet sheets draped over their shoulders in freezing temperatures, using only body heat generated by thought. Scientists studying this phenomenon have found that certain meditation practices can influence the autonomic nervous system, regulating heart rate, blood pressure, and even temperature. Brain scans show unusual patterns of activity during these states, suggesting that years of disciplined practice can unlock access to bodily processes usually considered automatic. While few reach this level of mastery, the experiments reveal the astonishing reach of the mind over the body. The idea that focused thought alone can warm the flesh in icy winds feels almost superhuman, and yet it emerges from the same human brain we all share. It demonstrates the depth of untapped potential woven quietly into the folds of our minds. Daydreaming activates a special brain network. When your thoughts drift, you are not switching off, you are switching networks. Neuroscientists call it the default mode network, a constellation of brain regions that light up when you are at rest, not focused on the outside world. This network weaves together memories, imagines possible futures, and explores scenarios in a kind of inner simulation. Far from being idle, daydreaming is essential for creativity, problem-solving, and even empathy. It is during these moments of quiet drift that your brain knits experiences into stories, forming the narrative of your life. The wandering mind is not a distraction from reality, but an expansion of it, testing paths you have not yet walked. So the next time your attention slips, remember that your brain is busy in its own theater, painting landscapes, rehearsing futures, and weaving the fabric of your inner world. Memory is rewritten every time you recall it. We often imagine memory as a video archive, faithfully storing past events. But neuroscience reveals that memory is dynamic. Each time you recall an event, your brain reconstructs it from scattered fragments across different regions. In the process, details can be altered, forgotten, or even unintentionally replaced. This phenomenon, called reconsolidation, means that memory is less like a file and more like a story retold, changing subtly with each telling. It explains why eyewitness testimony can be unreliable or why cherished memories shift with time. But it also allows memories to be updated, softening trauma or reshaping learning. In a sense, the past is always alive, being rewritten in the present. Every memory you revisit is not a static recording, but a living narrative, adapted to who you are now, proving that your sense of history is itself a work of the imagination. Traumatic memories can alter the brain's physical structure. Severe trauma does not only haunt the mind, it imprints itself in the brain's anatomy. Post-traumatic stress disorder is associated with shrinkage of the hippocampus, heightened activity in the amygdala, and weakened control from the prefrontal cortex. These changes explain why traumatic memories can feel vivid, intrusive, and emotionally overwhelming. The brain essentially shifts into a state of hypervigilance, as if danger is always near. But research also shows that with therapy, support, and time, some of these structural changes can heal, with the hippocampus regaining volume and regulation pathways strengthening. Trauma reshapes the brain, but recovery reshapes it too. Each pathway altered by fear can be counterbalanced by new circuits of safety and resilience. The scars of trauma are written into neural tissue, but so too are the patterns of healing, a testament to the brain's enduring capacity for renewal. The brain can erase memories under certain conditions. Memory feels permanent, but in reality, it is fragile and malleable. Scientists have found that under certain conditions, particularly when memories are reactivated and enter a flexible state called reconsolidation, they can be altered, even erased. In animal studies, specific drugs given at the right moment can block a memory from being stored again, effectively deleting it. Though this research is still early, it raises both hopeful and troubling possibilities: the ability to weaken traumatic memories for therapy, or the risk of manipulating memory itself. Even without drugs, the brain sometimes erases memories naturally, pruning unused connections to make room for new learning. Forgetting is not a flaw, but a feature, a way to keep the mind uncluttered. It shows that memory is not etched in stone but written in sand, always subject to being reshaped, softened, or washed away entirely. Scientists can sometimes trigger lost memories with electrical stimulation. In certain neurosurgeries, when electrodes stimulate specific brain regions, patients suddenly recall vivid, long-forgotten memories. A woman may hear her childhood piano lessons as if they're happening again, or a man may relive standing on a familiar street corner decades earlier. These moments are not vague impressions, but detailed sensory recreations, complete with sounds, smells, and emotions. The effect suggests that even memories long thought forgotten may still exist in hidden neural traces, waiting for the right spark to bring them alive. This discovery reveals the depth of the brain's storage, a vast archive far larger than daily awareness can access. While science is far from being able to summon memories at will, these glimpses show that your past is not gone but slumbering, embedded in the folds of the mind, like books on an endless shelf waiting to be reopened. Memories can be strengthened during sleep with subtle cues. During sleep, your brain doesn't just rest, it consolidates memory, weaving the day's experiences into lasting form. Experiments show that memories can even be nudged stronger with subtle cues. In one study, participants learned a set of word pairs or spatial tasks while a specific sound or smell played. Later, when the same cue was softly presented during deep sleep, those memories became more robust, as if the brain rehearsed them unconsciously. This phenomenon, called targeted memory reactivation, highlights how the sleeping brain is actively at work, sorting, strengthening, and sometimes reshaping the day's information. It suggests that learning does not stop when you close your eyes. In fact, sleep may be the most important stage of all. The idea that a faint whiff of a scent or a soft tone can reach into the dreaming brain and solidify memory is both eerie and wondrous. The brain replays experiences like a movie during dreams. While you sleep, your brain is far from idle. Neurons fire in patterns that resemble waking activity, as if replaying the day's experiences like scenes from a film. In animals, scientists have recorded brain cells firing in the same sequence during sleep that they did while the animal explored a maze, compressed, like a time-lapse replay. In humans, dreams often echo fragments of recent life, stitched into surreal narratives. This replay is thought to help consolidate memory, reinforcing learning by reactivating the neural circuits involved. It's as though the brain is editing a movie of your life, splicing together the key frames and saving them to long-term storage. The result is both practical and poetic. The dream world serves as rehearsal and archive, taking the raw footage of waking and crafting it into something lasting, a record etched into the mind's hidden vaults. Dreams may be the brain's way of cleaning and reorganizing itself. Why do we dream? One intriguing idea is that dreams serve as the brain's nighttime housekeeping. By weaving strange stories, the brain may be testing associations, pruning weak connections, and strengthening useful ones. This process could explain why dreams often mix unrelated images or people. The brain is reorganizing memory networks, trying out combinations, discarding some, and keeping others. The bizarre narratives are a side effect of this deeper work. Some researchers also suggest that dreaming helps regulate emotion, replaying stressful events in safer symbolic forms. Whatever their exact purpose, dreams appear to be more than idle fantasy. They are the brain's nocturnal workshop, tuning its circuits, washing away the clutter of the day, and reorganizing the mind for clarity. The surreal landscapes of dreams may be the visible trace of a hidden process, the brain quietly tending to itself in the dark. Sleep helps wash away waste from the brain. During the day, your brain produces metabolic waste, including proteins linked to disorders like Alzheimer's. At night, something remarkable happens. The brain's cells shrink slightly, allowing cerebrospinal fluid to wash through the tissue, clearing away debris. This glymphatic system is like a nightly rinse cycle, flushing toxins and restoring balance. The process is so effective that a single night of poor sleep measurably increases waste buildup. This discovery highlights sleep's vital role not only in memory and mood, but in physical brain health. Just as the body needs rest to heal, the brain needs sleep to cleanse itself. When you drift into slumber, you are not only recharging energy, but also bathing the mind in its own silent tide, sweeping away what is no longer needed and leaving behind a refreshed, clearer landscape for the next day's thoughts to grow upon. The brain shrinks slightly during the day and re-expands at night. Your brain subtly changes size over the course of a single day. MRI scans reveal that the brain shrinks slightly during waking hours, compressed by the demands of activity, and then re-expands during sleep as it recovers. This rhythm reflects the ebb and flow of fluid, cellular activity, and metabolic processes, a daily tide within the skull. The changes are tiny, fractions of a percent, but significant enough to be measurable. It may be one reason why you feel foggy after long days and refreshed after rest. Your brain has literally shifted shape, contracting under the strain of wakefulness and swelling gently back during slumber. This cycle reminds us that the brain is not static stone, but living tissue, constantly in motion, pulsing with fluids, expanding and shrinking like the tide, following the quiet rhythms of day and night. Your brain keeps working while you sleep. Far from switching off, your brain stays busy when you sleep. It sorts through memories, regulates hormones, fine-tunes immune responses, and rehearses skills learned during the day. Certain stages of sleep, like REM, are especially active, with brain activity resembling wakefulness. This hidden labor explains why sleep deprivation so quickly affects mood, memory, and health. It also explains the flashes of creativity or sudden clarity that sometimes greet you upon waking. The brain has been solving problems in the background. In this sense, sleep is less about shutting down and more about shifting modes from external engagement to internal maintenance. Every night, as the body lies still, the brain is a quiet workshop, repairing, reinforcing, and reorganizing. It reminds us that rest is not idleness, but an essential part of being alive, where the unseen work of the brain prepares you for another day. The brain produces psychedelic states on its own, even without drugs. Psychedelic visions are not confined to substances. The brain can generate them spontaneously. Under conditions like sensory deprivation, fasting, meditation, or even illness, people sometimes report vivid geometric patterns, lights, or mystical experiences. Scientists suggest these arise when normal brain rhythms become disrupted, allowing deeper networks to spill chaotic imagery into consciousness. Remarkably, these experiences often involve the same neural pathways engaged by psychedelic drugs, showing that the potential for such visions exists in everyone. The kaleidoscope of the mind is built in, waiting under the surface. This may explain why cultures across history have described visions during trance, prayer, or near-death experiences. The brain itself carries the seeds of altered states, capable of producing worlds of light, color, and meaning, without any external catalyst. The capacity for wonder, woven into neural tissue, is part of what makes consciousness so strange and profound. Some people can control their dreams with lucid dreaming. Lucid dreaming is the rare ability to realize you are dreaming while the dream continues. With practice, some people can even shape the dream, flying through imagined skies or speaking with dream characters. Neuroscientists find that lucid dreaming involves unusual activity in the prefrontal cortex, the part of the brain linked to self-awareness and control. Training methods, like reality checks during the day or setting intentions before sleep, can increase the likelihood of lucid dreams. These experiences feel astonishingly real, blending the vividness of dreaming with the clarity of waking. For some, lucid dreaming is simply playful exploration. For others, it is a tool for creativity, therapy, or overcoming nightmares. The idea that you can awaken inside your own dream, steering the story of the night, shows just how thin the boundary is between reality and imagination within the brain. Your brain holds more connections than all the stars in the Milky Way. Inside your skull is a network so vast it defies comprehension. The human brain contains roughly 86 billion neurons, and each of those can form thousands of connections called synapses. Altogether, the number of connections reaches into the hundreds of trillions, more than there are stars in the Milky Way galaxy. These connections are not static. They strengthen, weaken, or vanish depending on experience, forming the ever-changing map of who you are. Every thought, memory, and skill depends on patterns across this astronomical web. It is humbling to realize that the night sky, filled with stars beyond counting, is mirrored in miniature inside each of us. The scale suggests that the brain is not just an organ, but a cosmos of its own, a galaxy of living connections, endlessly shifting, flickering, and weaving the story of your life. The brain generates hallucinations without any external stimulus. Hallucinations are not always caused by drugs or illness. Sometimes the brain produces them on its own. In sensory deprivation chambers, people often begin to see lights, patterns, or hear phantom sounds after only hours. Patients with Parkinson's disease may glimpse small animals or figures that aren't there. Even healthy individuals can experience hypnagogic hallucinations as they fall asleep, vivid images and sounds conjured entirely by the brain. These experiences happen because perception is not a direct window onto reality. It is a construction, assembled from incoming signals and the brain's predictions. When input falters or circuits misfire, the brain fills the gap with its own creations. Hallucinations remind us that consciousness is not a fixed recording of the world, but a living, generative process. At times, the brain becomes its own projector, casting images onto the screen of awareness without any world outside. A jolt of electricity can change your mood in seconds. The brain runs on electricity, and even a tiny current in the right spot can alter how you feel. In clinical settings, direct stimulation of certain brain regions has been shown to lift depression almost instantly, replace despair with laughter, or spark intense calm. Transcranial magnetic stimulation, which uses pulses of magnetic fields, can similarly nudge mood and cognition. These treatments are being explored as therapies for disorders resistant to medication, offering new hope for people who suffer from chronic depression or anxiety. The effects can be startling. Sadness evaporates, joy appears, or fear dissolves, all from a few seconds of electrical influence. While the brain is a seat of identity, these experiments show that emotions, which feel so deeply personal, are also products of physical circuits. A shift in electricity can ripple into the mind's most intimate experiences, transforming perception and mood in an instant. Placebos can trigger real brain chemistry changes. The placebo effect is not just all in your head, it is literally in your brain. When someone believes a treatment will help, their brain often responds by releasing real chemicals that mirror the expected effect. Placebo painkillers can prompt the brain to release endorphins, natural opioids stronger than many drugs. Placebo antidepressants can adjust serotonin pathways, lifting mood. In brain scans, these effects are visible. The same circuits that respond to medicine often respond to belief. The placebo effect highlights how expectation and trust are powerful biological forces, able to shape perception, pain, and healing. It blurs the line between mind and body, showing that belief itself is a kind of medicine. The brain is not just a passive recipient of treatment, but an active participant in healing, capable of summoning its own pharmacy when the story of relief is convincing enough. The brain creates its own painkillers stronger than morphine. Hidden in your brain are natural opiates, chemicals that dampen pain and generate calm. Called endorphins and enkephalins, these molecules bind to the same receptors targeted by morphine, sometimes producing effects even stronger. They flood the body during exercise, laughter, and moments of stress, acting as an internal shield. The runner's high is one example, a euphoric state where pain melts into exhilaration as endorphins surge. Similarly, people in emergencies sometimes report not feeling injuries until long afterward, when the brain's natural painkillers wear off. These systems evolved to help humans survive danger and hardship, masking pain long enough to escape or fight. It means that your brain carries its own pharmacy, ready to release powerful medicine when needed. Every moment of relief, joy, or endurance may be traced back to these quiet molecules, shimmering in your brain's hidden chemistry. The same brain circuit fires for physical and emotional pain. Heartbreak feels like it hurts, and in a way, it does. Neuroscientists have found that the same brain regions that light up when you stub your toe or burn your hand also activate when you experience rejection, grief, or social loss. The anterior cingulate cortex and insula, key centers for pain processing, don't distinguish much between the sting of the body and the ache of the heart. This overlap suggests that social bonds are as vital to survival as avoiding physical harm. Evolution may have wired emotional pain into the same circuits to ensure we stay connected. It explains why loneliness and loss feel physically crushing, and why painkillers can sometimes soften emotional suffering. The discovery reveals how deeply entangled the physical and emotional worlds are. In the brain, pain is not only a sensation, but a signal of connection broken. Laughter activates multiple regions across the brain at once. Laughter may feel effortless, but it is one of the most complex acts the brain performs. It engages the prefrontal cortex, which processes context and humor, the limbic system, which handles emotion, and the motor cortex, which coordinates the rhythmic movements of breath and voice. Brain scans show that laughter is not confined to a single spot, but lights up circuits across the mind in a joyful cascade. This wide activation may be why laughter feels so freeing. It synchronizes many regions at once. Laughter also floods the brain with endorphins, lowering stress and boosting connection. It is social glue, bonding people together through shared rhythm. The act that feels spontaneous and light-hearted is, in fact, a symphony of neural activity. Every chuckle is a full-brain performance, reminding us that joy is not just felt in the heart, but orchestrated in the brain. The brain's mirror neurons make you feel others' emotions. When you see someone smile, your brain doesn't just recognize it, it partially mirrors it. Special cells called mirror neurons fire when you perform an action and when you see someone else perform it. They are thought to underlie empathy, allowing you to feel echoes of others' emotions. This is why watching someone cry can make your own throat tighten, or seeing a yawn can trigger one in you. Mirror neurons blur the boundary between self and other, weaving invisible threads of connection. They may have been crucial for learning and social bonding, letting humans share skills and feelings across a group. While their exact role is still debated, the idea is profound, that much of what you feel is not only your own, but a reflection of the world around you. Your brain is, in many ways, an empathetic mirror. The brain can generate a sense of time that speeds up or slows down. Have you noticed how time seems to stretch during moments of fear or collapse into flashes during joy? This distortion is born in the brain. Internal clocks, distributed across regions like the basal ganglia and cerebellum, constantly track intervals. But emotion, attention, and arousal warp the signals, making seconds feel longer or shorter than they are. In emergencies, the brain lays down more detailed memories, creating the impression that time has slowed. In flow states, playing music, painting, or running, the opposite happens, and hours vanish in what feels like minutes. Time is not absolute in the mind, but elastic, bent by circumstance and feeling. The physics of the clock may march steadily, but the brain's time is fluid, stretching and compressing to fit the landscape of experience, making every moment uniquely human in its texture. Bilingual brains grow denser gray matter than monolingual brains. Speaking more than one language does more than expand communication, it reshapes the brain itself. Bilingual individuals often show greater density of gray matter in regions linked to memory, attention, and executive control. Constantly switching between languages strengthens the brain's flexibility, improving multitasking and focus. It also seems to protect against cognitive decline, delaying the onset of dementia in some studies. The act of juggling vocabularies and grammar builds resilience into the mind, like a workout for neural circuits. Even learning a new language later in life can spark growth, proving the brain never loses its capacity to change. The benefits extend beyond linguistics. Bilingual brains tend to show sharper problem-solving skills and more adaptable thought patterns. Each word learned is not just a tool for speaking, but a brick in the architecture of a stronger, more resilient brain. Reading activates nearly the entire brain at once. When you read a sentence, it feels effortless, almost automatic. But inside, your brain is performing a symphony of activity. The visual cortex decodes the shapes of letters, language centers in the temporal lobe process, meaning the prefrontal cortex organizes comprehension, and even motor regions subtly engage, as if rehearsing D. the motions of speech. Reading can also stir emotional areas, lighting up memory and imagination as you picture scenes and feel characters' emotions. In this way, reading is one of the few activities that recruits nearly the entire brain. Each page is not just ink on paper, but a workout across vision, language, memory, and empathy. It explains why reading strengthens cognition and why stories feel so immersive. They enlist the whole brain in creating an inner world. The act of following words on a page is, in truth, a full brain experience. Every thought you have leaves a physical trace in your brain. Thoughts may seem intangible, but each one leaves behind a physical imprint. When neurons fire together, their connections strengthen slightly, a process often summed up as cells that fire together, wire together. Over time, repeated thoughts or habits carve pathways into the brain, making them easier to recall or repeat. This is why practicing gratitude can change mood, or why rehearsing skills makes them second nature. Even fleeting ideas spark microscopic adjustments in synapses. The brain is like clay, reshaped moment by moment, molded by the currents of consciousness. It means that who you are today is built from the accumulation of your thoughts, each leaving a trace on the living tissue of your mind. Nothing is lost. Every passing idea contributes to the architecture of self, etching a delicate, invisible history into the brain's vast network of connections. Brains of extreme athletes show special adaptations to fear. Free solo climbers, big wave surfers, and wingsuit flyers appear fearless in situations most would find overwhelming. Brain scans reveal that these extreme athletes often have unusual patterns of activity in their amygdala, the fear center of the brain. Instead of showing heightened responses, their amygdalas remain calmer, allowing them to act with focus where others might freeze. Some of this may be innate, but much is also trained. Repeated exposure to danger conditions the brain, teaching it to regulate fear and channel adrenaline. These adaptations give them an edge, letting them perform with clarity in life-threatening environments. It doesn't mean they lack fear entirely. Rather, their brains process it differently, translating it into calm concentration. These findings show that even the most primal emotions, like terror, can be reshaped by experience, sculpting the mind into something astonishingly resilient under pressure. Some brains solve math problems by recruiting visual regions. Not everyone's brain tackles math in the same way. In some people, solving equations activates not just traditional numerical regions, but also areas devoted to vision and spatial reasoning. They may see numbers as shapes, arrange calculations as mental diagrams, or imagine equations as movements in space. This visual approach can give them unique strengths, allowing rapid problem-solving or intuitive leaps that feel less like calculation and more like perception. Brain scans confirm that these individuals light up the occipital cortex, normally reserved for sight, while working through math. It suggests that mathematical thought is not confined to a single brain circuit, but can recruit many pathways, depending on the individual. Numbers are not just abstract symbols, but flexible tools, and the brain adapts to use them in whatever way it can. For some, math is not only logic, but a kind of inner vision. Extreme memory champions use brain tricks anyone can learn. People who compete in memory championships seem superhuman, memorizing thousands of digits or entire decks of cards in minutes. Yet most of them are not born with unusual brains. Instead, they use ancient techniques like the memory palace, where information is stored as vivid images placed along an imagined path through a familiar building. Brain scans show that when they perform these feats, regions linked to spatial navigation are unusually active, as if they are walking through mental landscapes filled with symbolic objects. This method works because the brain is naturally wired to remember places and images far better than raw numbers. With practice, Anyone can improve memory this way, though few reach championship levels. These findings prove that extraordinary memory is less about innate talent and more about harnessing the brain's hidden strengths, turning recall into a creative act of imagination. The brain can restructure entirely after just weeks of practice. It might seem that meaningful brain change takes years, but scans reveal that just weeks of practice can leave a measurable imprint. Learning to juggle, for example, has been shown to increase grey matter in regions linked to hand-eye coordination after only a month. Language learning, music lessons, or even memory exercises can spark similar changes. This rapid remodeling underscores how sensitive the brain is to training and repetition. Circuits expand to meet demand, like muscles growing with exercise. Even short bursts of dedicated effort reshape the architecture of the mind. The discovery is empowering. Change does not require decades. With consistent practice, the brain begins rewiring itself almost immediately. The mind is a dynamic organ, always adapting, capable of growth at any stage of life. Every new skill learned leaves behind structural echoes, proof of the brain's extraordinary capacity for transformation. The brain's plasticity makes each person's path of growth unique. Though all human brains share the same basic structure, each one grows and adapts in a way no other does. Plasticity, the brain's ability to rewire, means that your experiences, habits, and environment carve unique patterns of connectivity. Even identical twins with the same DNA develop distinct brains as they live different lives. This uniqueness explains why people vary so widely in talents, memories, and even vulnerabilities. Every choice you make, from hobbies to friendships to challenges overcome, reshapes the neural map. Far from being fixed, the brain is a personal creation, sculpted by living. It means there is no single blueprint for growth. Your brain's pathways are as individual as your fingerprints. The story of your life is literally written into its folds, making your mind a one-of-a-kind landscape, shaped by the experiences only you have walked. The brain sometimes moves your body before you decide to. When you reach for a cup or press a button, it feels like your conscious will drives the action. But experiments show that the brain's motor regions begin preparing movements fractions of a second before you become aware of deciding. In the famous Libet experiment, brain activity predicting a choice appeared hundreds of milliseconds before participants reported making it. This suggests that consciousness may not initiate action but narrate it afterward, weaving the sense of free will into a story. While the debate is ongoing, the findings raise profound questions. How much of what we do is chosen, and how much is prepared unconsciously? Rather than diminishing human agency, it may highlight how deeply integrated conscious and unconscious processes are. You are not just a pilot at the controls, you are also the plane, the engines, and the sky through which decisions fly. Your conscious mind may only notice a fraction of what your brain does. Your conscious awareness is like the tip of an iceberg, visible, but tiny compared to the vast unseen below. Most brain activity happens outside awareness, regulating heartbeat, filtering sensory input, storing memories, and even shaping decisions before they surface. At any moment, the brain is processing millions of signals, but only a thin stream enters consciousness. This stream is enough to give you a coherent sense of self and world, but it is a fraction of the whole. Experiments show that choices, feelings, and perceptions often form unconsciously, with awareness arriving only after the fact. The conscious mind is more like a narrator than a controller, telling the story of what the larger brain has already set in motion. It is humbling to realize that the you know is only a small window onto the vast hidden theater of the mind. Brain scans can sometimes detect decisions before you're aware of them. In cutting-edge experiments, scientists have used brain scans to predict choices seconds before participants became conscious of deciding. For example, by monitoring activity in the prefrontal and parietal lobes, researchers could forecast whether someone would press a left or right button long before they reported making the choice. This doesn't mean free will is an illusion, but it does suggest that decisions arise gradually, shaped by unconscious activity that bubbles up into awareness. Consciousness may be the final stage in a longer chain, the moment the brain's hidden debate crosses a threshold. These studies blur the line between thought and action, raising deep questions about control and identity. If your brain knows before you do, then who exactly is the you that decides? Perhaps selfhood is not a single voice, but the culmination of countless neural murmurs converging into awareness. The brain processes images faster than the blink of an eye. Your eyes take in information constantly, but it's your brain that makes sense of the flood. Astonishingly, research shows the brain can process a visual image in as little as 13 milliseconds, far faster than the time it takes to blink. This lightning speed allows you to recognize a friend's face in a crowd or catch sight of a bird darting across the sky almost instantly. The brain's visual system works in parallel, with different regions decoding color, motion, shape, and depth simultaneously before stitching the pieces into a coherent scene. The efficiency is so high that you often identify objects before you are fully aware of seeing them. This rapid-fire perception reveals how evolution has honed the brain for survival, giving humans the ability to react to the world in real time. Each glance is a silent miracle of speed and precision. The brain produces tiny magnetic fields with every thought. Every time neurons fire, they create not only electrical signals, but also faint magnetic fields. These fields are unimaginably small, a billion times weaker than Earth's magnetic field, yet sensitive instruments like magnetoencephalography (MEG) can detect them outside the skull. By measuring these whispers of magnetism, scientists can map brain activity with remarkable precision, capturing millisecond by millisecond changes. It means that every thought, every flicker of memory or dream leaves a magnetic trace in the air around your head. These signals are so delicate that they require rooms shielded from all other electromagnetic noise to measure. The existence of these fields underscores the brain's dual nature as both a biological and a physical system, humming with electricity and magnetism. Even though you cannot feel them, the magnetic echoes of your thoughts shimmer constantly, invisible halos radiating from the most mysterious organ you carry. The brain feels no pain. Paradoxically, the organ that generates your experience of pain cannot feel pain itself. Surgeons can operate on the brain while patients are awake, and though the surrounding tissues of the scalp and skull are sensitive, the brain's neurons lack pain receptors. This is why neurosurgery can be performed with patients fully conscious, helping doctors map brain regions by asking them to speak, move, or even laugh during the procedure. It also explains why headaches don't originate from brain tissue but from surrounding structures like blood vessels, muscles, and membranes. The brain is exquisitely sensitive to temperature, pressure, and chemistry in terms of function, but numb to pain in its own tissue. This strange fact underscores the difference between perceiving pain and generating it. The brain is the conductor of the symphony of sensation, but its own instrument remains curiously silent. The brain has a default mode network that lights up when you daydream. When your mind wanders, drifting to past memories, imagining the future, or rehearsing conversations, a special set of regions called the Default Mode Network, DMN, comes alive. This network, spanning the medial prefrontal cortex, posterior cingulate cortex, and other areas, is less active during focused external tasks but lights up during introspection. Far from being idle, the DMN is thought to weave the threads of your personal narrative, maintaining a sense of self across time. It links memory to imagination, helping you simulate possible futures and reflect on meaning. The discovery of the DMN reshaped neuroscience, showing that the brain's resting state is actually one of its busiest. Daydreaming, often dismissed as distraction, turns out to be essential for creativity, self-reflection, and problem-solving. When your thoughts wander, your brain is not switching off. It is exploring the inner landscapes that make you who you are. Certain brainwaves may synchronize across groups of people. When people gather, their brains may subtly align. Studies using EEG have found that individuals watching the same movie, listening to music, or engaging in conversation can show synchronized brainwave patterns. This phenomenon, sometimes called neural coupling, suggests that shared experiences literally bring minds into rhythm. Teachers and students, performers and audiences, even groups of friends laughing together often show heightened synchronization, reflecting a shared focus and emotional connection. The effect may explain why collective experiences feel powerful, why music unites crowds, and why storytelling has such impact. In these moments, the boundaries between minds blur, as if individual brains become instruments in a larger orchestra of thought. The discovery reveals that human connection is not just metaphorical but measurable in brain rhythms, beating together in quiet harmony when we share attention, emotion, and presence. Brain cells talk not only with electricity, but with light-like flashes. Neurons communicate primarily with electrical impulses and chemical signals, but researchers have discovered that they may also emit tiny flashes of light. Known as biophotons, these ultra-weak photons are produced during certain chemical reactions in neurons. Though faint, they hint at the possibility of a light-based layer of communication in the brain. Some scientists speculate that these flashes might influence neural activity or serve as byproducts of metabolism, though their role remains mysterious. The idea that your thoughts could be accompanied by tiny sparks of light inside your skull is both poetic and profound. While much remains unknown, the discovery reminds us that the brain may harbor levels of communication still beyond our understanding. It is not only an electrical network, but perhaps a luminous one too, flickering with light-like whispers that illuminate the hidden depths of consciousness. The brain produces more than 80 different neurochemicals. The brain is a bustling chemical laboratory, generating a vast array of neurotransmitters and neuromodulators. These include familiar names like dopamine, serotonin, and oxytocin, but also dozens more with subtle, intricate roles, from regulating sleep and appetite to shaping mood, attention, and learning. Each chemical acts like a note in the symphony of the mind, balancing excitation and inhibition, sharpening focus or softening stress. The sheer number, over 80 known varieties, underscores the brain's complexity. It isn't powered by a single fuel, but by an orchestra of molecules, each binding to billions of receptors, orchestrating thought and feeling. The balance's delicate shifts in even one can ripple across the system, altering perception and behavior. This biochemical richness makes the brain adaptable, resilient, and sometimes unpredictable, a reminder that every mood or idea emerges from the invisible interplay of a molecular storm. Dopamine shapes your sense of motivation and reward. Often nicknamed the pleasure chemical, dopamine is better understood as the brain's signal for motivation and reward prediction. When you anticipate something good, a delicious meal, a text from a loved one, or the satisfaction of completing a task, dopamine surges, nudging you forward. It doesn't just make you feel good, it wires motivation into action, teaching the brain which behaviors are worth repeating. Too little dopamine can sap drive and focus, while too much can fuel compulsions or risky behavior. Dopamine's influence stretches from habit formation to addiction, from everyday satisfaction to long-term goals. It is the brain's way of tagging certain experiences with a bright marker. This matters. Far from being a simple pleasure switch, dopamine is the architect of effort and desire, shaping the pursuit of joy and weaving motivation into the rhythm of daily life. Oxytocin can change how much you trust someone. Known as the bonding hormone, oxytocin flows during hugs, childbirth, and moments of closeness. In the brain, it enhances trust, empathy, and social connection. Experiments show that people given oxytocin are more likely to cooperate, share, or take social risks. It is one of the key molecules that turn relationships into lasting bonds, weaving the invisible ties of family, friendship, and love. But oxytocin is not universally good. It can also increase in-group favoritism, sharpening the divide between us and them. This dual role reveals its evolutionary purpose: to foster trust within close groups, strengthening survival, even at the cost of suspicion toward outsiders. Oxytocin's effects remind us that biology shapes even our deepest feelings of connection. Every warm embrace, every surge of trust, every bond of love is supported by this small but mighty chemical messenger, whispering through the brain. Serotonin influences mood, sleep, and appetite all at once. Serotonin is one of the brain's most versatile chemicals, influencing mood, sleep cycles, digestion, and even perception. Balanced serotonin levels are linked to feelings of calm and well-being, while imbalances are associated with depression and anxiety. It plays a crucial role in regulating appetite and sleep, helping the body maintain steady rhythms. Some psychedelic substances work by mimicking serotonin, altering perception in profound ways. About 90% of the body's serotonin is produced in the gut, highlighting the deep connection between digestion and mood, the so-called gut-brain axis. Serotonin demonstrates how no single function in the brain is isolated instead. One molecule can influence many aspects of life simultaneously. Each moment of contentment, every smooth night of rest, every appetite for food or experience is shaped, in part, by serotonin's quiet orchestration, linking mind and body in a shared chemical rhythm. The brain stores languages in different locations depending on age learned. If you learn a second language as a child, your brain tucks it into the same region as your first, weaving the two together seamlessly. But if you learn later in life, the new language is stored in a slightly different area, neighboring but distinct. This separation explains why children can switch between languages effortlessly, while adults may struggle to suppress interference from their native tongue. Brain scans confirm that the timing of exposure shapes the architecture of language storage, highlighting the brain's flexibility during development. Early learning integrates languages into a single system. Later learning builds parallel but separate circuits. This discovery shows how the brain's plasticity changes with age, and why childhood is such a golden window for language. It also underscores that even in adulthood, the brain remains adaptable, constructing fresh neural maps to house new words and worlds. The brain processes your inner voice like external speech. That silent voice in your head, the one that reads words, replays conversations, or plans what to say, is treated by your brain much like actual sound. Neuroimaging shows that inner speech activates auditory and language processing areas, as though you were hearing your own words. This is why inner dialogue can feel so vivid, and why the brain can sometimes confuse imagined voices with real ones, as in certain psychiatric conditions. The inner voice plays a crucial role in memory, planning, and self-regulation, giving thought a structured, verbal shape. Far from being an abstract phenomenon, it is a concrete process, echoing through auditory circuits. Every time you talk silently, your brain rehearses sound without producing it, weaving language into thought. In a sense, you are always both the speaker and the listener in your own mind, narrating life's unfolding moment by moment. The teenage brain rewires itself in waves of change. Adolescence is not just a storm of hormones, but a profound neurological remodeling. During the teenage years, the brain prunes excess synapses, streamlining connections for efficiency, while simultaneously strengthening circuits linked to decision-making, social interaction, and emotional regulation. These changes occur unevenly. The limbic system, which processes emotion and reward, develops earlier, while the prefrontal cortex, responsible for judgment and impulse control, matures later. This imbalance explains the thrill-seeking, risk-taking, and intensity of teenage behavior. Far from being flaws, these shifts prepare the brain for adulthood, fostering flexibility, learning, and independence. The rewiring unfolds in waves, making adolescence a period of both vulnerability and incredible potential. What looks like chaos is, in fact, the brain reorganizing itself into a more powerful, efficient machine, laying down the architecture that will carry a person through the rest of their life. The brain doesn't finish developing until the mid-20s. While bodies reach physical maturity in late adolescence, the brain continues developing well into the mid-20s. The prefrontal cortex, the seat of planning, reasoning, and impulse control, is one of the last regions to fully mature. This extended timeline explains why young adults may still struggle with long-term decision-making or risk assessment, even though they appear fully grown. It also highlights the flexibility of early adulthood, a period when the brain is still refining pathways for judgment, empathy, and self-control. Far from being static, these years represent the final stage of brain development, blending youthful adaptability with the stability of maturity. Knowing this can reframe how we view the challenges of early adulthood, not as failures, but as part of the natural process of the brain completing its masterpiece. By the mid-20s, the architecture of thought finally settles into place. Infant brains build up to 1 million new connections per second. In the first years of life, the brain grows at a staggering pace. Each second, up to 1 million new synaptic connections bloom between neurons, weaving the foundations of perception, language, and movement. This explosive growth is fueled by the infant's constant absorption of the world. Every sound, sight, and touch etches itself into neural architecture. By age 3, a child's brain has far more synapses than an adult's, a lush network later refined through pruning. This early abundance explains the extraordinary learning capacity of young children, who pick up languages, motor skills, and patterns with ease. It is a period of breathtaking neural construction, as though the brain were racing to lay down every possible pathway, ensuring survival and adaptability. The pace may slow later, but the early years leave lasting imprints, shaping the foundations of intelligence and personality for a lifetime. Babies are born with nearly all the neurons they'll ever have. At birth, an infant already carries around 86 billion neurons, nearly the full lifetime supply. What changes dramatically after birth is not the number of neurons, but the connections between them. Synapses sprout rapidly as the baby encounters the world, linking neurons into networks that support perception, movement, and language. The sheer number of neurons at birth provides the raw potential, but experience sculpts the pathways, deciding which circuits flourish and which are pruned away. This balance of abundance and refinement gives human beings their remarkable adaptability, allowing each child to grow into their unique environment. The fact that nearly all neurons are present at birth is a reminder that the brain arrives prepared for a lifetime of learning. Not empty, but primed with enormous potential, waiting for the world to shape the dense forest of connections that define thought. a child's brain is far more flexible than an adult's. Children can recover from injuries, adapt to new environments, and learn skills in ways that adults often cannot. This extraordinary flexibility comes from heightened neuroplasticity, the brain's ability to rewire itself. For example, if a child suffers damage to one hemisphere, the other can sometimes take over lost functions, a feat far harder in adults. Languages learned in childhood integrate seamlessly, while adults struggle with accent and fluency. The child's brain is like wet clay, easily molded by experience, while the adult brain is more like hardened pottery, still adaptable but less fluid. This plasticity comes at a cost. Children may be more vulnerable to negative environments, as their brains absorb influences deeply. Still, the flexibility of the child's mind explains their astonishing capacity for growth and adaptation, shaping individuals into unique reflections of both biology and experience. Older brains still grow new neurons in certain regions. For much of the 20th century, scientists believed adults could not grow new neurons. But research has overturned this dogma, showing that neurogenesis continues into old age, especially in the hippocampus, a region central to memory and learning. These new neurons may help preserve cognitive flexibility, supporting the ability to adapt, learn, and form new memories even later in life. Exercise, enriched environments, and even meditation have been shown to encourage neurogenesis, suggesting practical ways to nurture the aging brain. While the overall rate of growth slows compared to childhood, the fact that it persists at all is remarkable. It means the brain is never fully fixed, but always evolving, even in advanced years. This discovery redefines aging, not as inevitable decline, but as a stage where growth, renewal, and change still quietly unfold inside the mind. Some people maintain brilliant cognitive abilities into very old age. While many associate aging with mental decline, some individuals, often called super-agers, retain exceptional memory, focus, and problem-solving skills well into their 80s or 90s. Brain scans reveal that super-agers often have thicker cortices and stronger connectivity in regions related to attention and memory, resembling the brains of much younger people. Lifestyle factors such as physical activity, social engagement, lifelong learning, and resilience may contribute, but genetics also play a role. Super-agers challenge the assumption that decline is inevitable, showing that some brains not only endure but thrive with age. Their stories are inspiring reminders of the brain's resilience. Even as years accumulate, the mind can remain sharp, agile, and luminous. Each super-ager is living proof that the brain's journey does not follow a single path. For some, it continues to sparkle brilliantly, long after most expect it to fade. Alzheimer's disease slowly dismantles neural networks. Alzheimer's disease is one of the most devastating neurological conditions, progressively eroding memory, language, and reasoning. It begins with the buildup of amyloid plaques and tau tangles, toxic proteins that disrupt communication between neurons. As networks break down, the hippocampus, the seat of memory, is among the first regions to falter. Over time, entire circuits collapse, leaving gaps in identity and awareness. What makes Alzheimer's so tragic is not only the loss of cognition, but the unraveling of the self as memories and personality fade. Yet research also highlights resilience. Some brains develop plaques without symptoms, hinting at protective factors still being uncovered. Understanding Alzheimer's is a race against time, with scientists working to slow, prevent, or reverse its course. The disease reminds us of the brain's fragility, but also of its profound significance, the keeper of who we are. Some people's brains keep working for minutes after the heart stops. When the heart stops beating, most of the body shuts down almost instantly. But the brain lingers. In some cases, brain activity continues for several minutes after death, producing measurable waves that resemble those seen in deep sleep or meditation. A few people revived after cardiac arrest even report vivid awareness during the period when they were clinically gone, describing tunnels of light, voices, or an expanded sense of time. Scientists debate whether these experiences come from residual bursts of electrical activity, a brain in survival overdrive, or something more mysterious. What's certain is that the brain does not flick off like a switch. Instead, it fades gradually, continuing to spark and hum in its final moments. These afterglow patterns remind us that consciousness is not so tightly bound to the heartbeat, but lingers on, as if reluctant to fully release its hold. The brain can be fooled into thinking a fake rubber hand as your own. In the famous rubber hand illusion, a person rests their real hand out of sight, while a lifelike rubber hand sits in front of them. When both the hidden hand and the fake hand are stroked at the same time, the brain merges the signals. Within minutes, many people feel as though the rubber hand is their own. Some even flinch when it's threatened. This experiment reveals how malleable body ownership is. The brain constantly weaves sensory inputs into a seamless sense of self, but it can be tricked. The illusion shows that our feeling of embodiment is not fixed, but constructed moment by moment. By bending the rules, scientists have demonstrated how easily the brain can be persuaded to redraw the boundaries of the body. What feels like you is, in part, a fragile story your brain tells and can rewrite. The brain can fill in missing vision, creating a seamless reality. Your eyes contain a natural blind spot where the optic nerve leaves the retina, a hole in your vision. Yet you never notice it because your brain automatically fills in the missing patch with surrounding detail. This happens not only for the blind spot, but in broader ways. When information is missing or obscured, the brain invents plausible details to maintain the illusion of continuous perception. If part of a pattern is hidden, you still see it as whole. If letters are blurred, your mind supplies the missing shapes. The result is a seamless reality that feels complete, even though gaps are constantly being patched. This creative editing shows that perception is not a passive recording but an active construction. Every moment, the brain is quietly painting in the blanks, producing a world so smooth and convincing that you rarely realize it is partly imagined. People with certain brain lesions can't recognize faces, even loved ones. Imagine looking at your partner, your child, or your best friend and seeing only a stranger. This is the reality of prosopagnosia, or face blindness, often caused by damage to a small patch of the brain called the fusiform gyrus. People with this condition can see every feature, eyes, nose, mouth, but cannot assemble them into a recognizable whole. They may rely on voices, clothing, or mannerisms instead. Some describe faces as all the same. The most haunting part is that even deep emotional recognition can vanish. A loved one may feel unfamiliar. This reveals how specialized the brain is. A tiny area can govern the immense social skill of recognizing faces. For those who live with it, every introduction, every meeting, is like encountering someone new, even if it's someone they have known all their lives. Certain people can see auras around others due to brain perception quirks. Some people report glowing colors shimmering around bodies, often described as auras. While mystical explanations abound, science suggests that in at least some cases, this comes from neurological quirks. A condition called synesthesia can cause senses to blend, making emotions or personalities trigger color perceptions. In rare visual processing differences, bright halos can appear around edges, particularly in high-contrast situations. Migraine sufferers sometimes see shimmering lights or colored outlines, which may contribute to aura-like experiences. Though not everyone perceives them, these brain-based phenomena demonstrate how subjective vision can be. For those who experience them, the world is infused with extra layers of light and color, tied to perception rather than reality. Whether mystical, neurological, or somewhere in between, auras highlight how the brain can take ordinary sensory input and transform it into something vivid, strange, and deeply personal. The brain sometimes creates extra sensations that don't exist. Your brain can produce sensations, touches, sounds, even smells that arise from nowhere. This phenomenon, known as paresthesia or hallucination, reveals how perception is generated inside the nervous system, not merely received from the outside world. People may feel buzzing, tingling, or crawling on their skin without stimulus. They may hear phantom sounds, tinnitus, or smell odors that aren't there. These experiences occur when the brain misfires, activating sensory regions in the absence of input. They remind us that reality, as experienced, is a product of the brain's interpretation of signals, and that those signals can arise internally. Though sometimes unsettling, these phantom sensations underscore the creativity of the nervous system. The brain is not only a receiver but a generator, able to conjure entire sensory experiences from nothing, convincing enough that they can feel utterly real. Phantom pain can be reduced by watching a mirror illusion. Amputees often experience phantom limb pain, sensations of discomfort, cramping, or burning in a limb that no longer exists. One of the most effective treatments involves nothing more than a mirror. In mirror therapy, a patient places their intact limb beside a mirror, creating the illusion that both limbs are present. When they move the healthy limb, the brain interprets the reflection as the missing one, updating its body map. For many, this simple trick relieves pain, sometimes dramatically. The therapy works because the brain's representation of the body can be recalibrated through visual feedback. What the eyes report can override what the nerves insist. This elegant solution demonstrates how perception and reality are intertwined. Even the absence of a limb can be soothed by a carefully crafted illusion, proof of the brain's willingness to believe what it sees. The brain creates phantom limbs that feel real even when missing. After amputation, many people continue to feel the presence of the missing limb, sometimes with uncanny vividness. They may sense their fingers wiggling, their toes curling, or their hand resting on their lap, even though the limb is gone. These phantom limbs arise because the brain's map of the body, stored in the somatosensory cortex, does not immediately update. The neurons representing the missing part continue to fire, generating sensations as if it were still there. Over time, the brain may reorganize, but for many, the phantom persists, sometimes for years. This illustrates how the brain constructs the experience of the body internally, not simply from physical feedback. Your sense of embodiment is a neurological creation, and once established, it can outlast the body itself. Phantom limbs are a haunting but fascinating reminder of the mind's power to conjure presence from absence. Tiny strokes can permanently alter personality. Not all strokes are dramatic. Some are small, almost undetectable at first. Yet even tiny strokes, depending on location, can reshape personality in profound ways. A minor interruption in blood flow might affect the frontal lobes, leading to sudden impulsivity, loss of empathy, or flattened emotion. Others might spark irritability, apathy, or unusual fixation on routines. Families often notice the change first. A loved one feels different, somehow not themselves. These shifts reveal how closely identity is tied to specific neural circuits. We like to imagine personality as a stable essence, but it is also a fragile construction, built on the functioning of delicate networks of cells. Tiny strokes expose this hidden truth. Even subtle damage can tilt the balance of traits that define us, reminding us how much of who we are depends on the quiet health of the brain. The brain has specialized cells that map your physical environment. Inside your hippocampus are remarkable neurons called place cells. They fire only when you are in a specific location, essentially forming an internal map of space. Discovered in rats and later confirmed in humans, these cells allow you to know where you are in a room, a city, or even a maze of hallways. Related cells called grid cells provide a coordinate system, laying out the geometry of your surroundings. Together, they give the brain a built-in GPS. This system explains how you can navigate familiar places without thinking, or suddenly recall a layout after years. It is also why damage to the hippocampus can cause disorientation, stripping away the brain's spatial compass. These specialized cells show that memory and navigation are intertwined. To know where you are is to know where you've been, and the brain records it with extraordinary precision. The brain's hippocampus acts like a time machine for memory. Deep within your brain, the hippocampus weaves together experiences into memory. When you recall the past, it doesn't simply retrieve a recording, it rebuilds the moment, piece by piece, like replaying a film. Scientists have found that hippocampal activity during recall mirrors its activity during the original event, as though it time travels back to the experience. This is why memories feel immersive. You don't just know what happened, you relive it. The hippocampus is also critical for imagining the future. Damage to it not only erases memory, but prevents people from picturing tomorrow. Past and future are built on the same mechanism, recombining fragments of experience. In this way, the hippocampus serves as your personal time machine, carrying you backward into yesterday and forward into the realm of possibility. Without it, you would be stranded in the present, unable to travel through your own life. Some people can remember events from the womb. It sounds impossible, but some people report vivid memories of sensations from before birth. Scientists once dismissed these as imagination, but research shows that late-stage fetuses can indeed form memories, responding to sounds, music, or voices they hear repeatedly in the womb. After birth, newborns recognize these sounds, calming at their mother's voice or familiar melodies. In rare cases, adults claim to recall these early impressions consciously. These prenatal memories are controversial, but they highlight the brain's astonishing ability to encode experience even before we breathe air. Whether remembered directly or imprinted unconsciously, the womb leaves its mark, a soundscape of muffled voices, rhythmic heartbeats, and surrounding warmth. Such claims remind us that memory begins earlier than we imagine, and that the brain, even before birth, is already a collector of time, tucking away impressions of the first world we ever know. The brain produces waves strong enough to be detected outside the skull. Your brain never stops humming with electricity. Neurons fire in synchronized rhythms that produce measurable oscillations or brainwaves. These patterns, alpha, beta, theta, delta, reflect states of thought, rest, and sleep. What's remarkable is that these waves are strong enough to be recorded from outside the skull, using techniques like EEG. Electrodes on the scalp pick up the faint currents, translating brain activity into visible waves on a screen. Even without direct contact, sensitive instruments can detect magnetic fields generated by neural firing. This means that, in principle, the hidden rhythms of thought extend beyond the body, radiating softly into space. While they cannot be read like an open book, The fact that our inner states have outward ripples is astonishing. Every thought, dream, and sensation sends faint echoes into the world, tiny signals of the brain's endless electrical symphony. Scientists have reconstructed sounds based on brain activity. Imagine hearing music that exists only in someone's mind. Neuroscientists are edging toward this possibility. By analyzing brain activity patterns when people listen to specific words or sounds, researchers have managed to reconstruct rough versions of what they were hearing. In some experiments, computer models trained on brain signals could generate recognizable speech from neural data alone. The reconstructions are imperfect, ghostly, and distorted, like hearing through static, but they hint at a future where inner experiences might be translated outward. This technology could someday give voice to people unable to speak by decoding the words forming silently in their minds. It also raises deep questions. If thoughts can be reconstructed, where is the boundary between mind and machine? For now, the idea that electrical pulses in the brain can be reshaped into audible sound feels like science fiction slipping into reality. The brain sometimes produces sudden flashes of insight out of nowhere. Every so often, a solution or idea erupts into awareness fully formed, as if delivered by lightning. These aha moments occur when different brain regions suddenly synchronize. Studies show that just before an insight, activity in the temporal lobe spikes, while the brain's rhythms shift toward gamma waves. In that instant, disparate ideas are woven together into a new whole. The experience feels magical because it bypasses conscious reasoning. The answer simply appears. Many creative breakthroughs, from scientific discoveries to artistic inspiration, have been born from such flashes. The brain seems to have a backstage workshop, quietly combining fragments until the curtain lifts. These moments remind us that thinking is not always deliberate. Sometimes, the greatest leaps arrive unbidden, like gifts. The mind works in silence, and then, all at once, offers up a spark that can change everything. The brain lights up differently when you're in love. Love isn't just an emotion. It is a whole brain event. Scans show that when people are in love, regions tied to reward, motivation, and pleasure, especially the caudate nucleus and ventral tegmental area, ignite with activity. Dopamine, the brain's feel-good chemical, surges, producing euphoria, craving, and focus on the beloved. At the same time, regions tied to judgment and negative emotions quiet down, explaining the rose-colored glasses effect. In long-term bonds, another network emerges, oxytocin and vasopressin circuits that foster trust and attachment. The pattern of activation shifts from fiery obsession to steady companionship. To the brain, love is not abstract. It is chemistry, wiring, and circuits working in concert. Yet what emerges from this web of activity feels larger than biology, a force that reshapes perception, fuels devotion, and gives human life its most profound connections. Babies' brains double in size during the first year of life. At birth, a baby's brain is only about a quarter of its eventual adult size. Yet within a single year, it doubles, exploding with new connections at a rate unmatched later in life. Neurons branch into dense forests of synapses, laying down the foundations for movement, language, and social understanding. A baby forms up to 1 million new connections per second, sculpted by experience. Every touch, sound, and smile builds the architecture of the mind. By age 3, the brain has twice as many synapses as an adult's, a surplus that will later be pruned back for efficiency. This early overgrowth ensures that infants can adapt to whatever environment they are born into. The astonishing growth of the first year reveals how the brain is not just pre-programmed, but actively shaped by the world, a living construction project built at dazzling speed. Some brains can withstand extreme injury yet still function. There are remarkable cases of people living with catastrophic brain injuries and functioning far better than anyone expected. One famous man lived a normal life despite missing most of his cerebral cortex, his skull largely filled with fluid. Others have survived with only half a brain, yet learned to walk, talk, and even attend school. This resilience comes from neuroplasticity, the brain's ability to reorganize itself. When one region is damaged, other areas can sometimes take over its functions, especially in children. Though limits exist, these stories reveal an astonishing adaptability. The brain is not rigid hardware, but a flexible network, capable of rerouting itself when under pressure. Such survival defies intuition. We imagine the brain as fragile, yet it is also deeply robust, able to endure loss and still sustain the spark of consciousness against extraordinary odds. Your brain is the most complex known structure in the universe. Across the cosmos, we find galaxies, nebulae, and stars. But nothing we know rivals the intricacy of the human brain. It contains around 86 billion neurons, each connecting to thousands of others, forming trillions of synapses. The number of possible connection patterns exceeds the number of atoms in the observable universe. Within this labyrinth lies consciousness, awareness, thought, memory, imagination. No other known structure packs so much density of function into such a small space. The brain is not only a receiver of the world, but a creator of inner worlds, capable of art, science, and reflection. To call it complex feels insufficient. It is a living universe of connections, endlessly dynamic. As far as we know, no star system or black hole rivals the mystery of what rests quietly inside your skull, a cosmos folded into flesh. Your brain is still a mystery, and may always be. After centuries of study, the brain remains the most profound riddle in science. We can measure its chemistry, map its circuits, and even watch it light up in real time. Yet the central question, how electrical pulses give rise to the feeling of being alive, is unsolved. Consciousness, identity, imagination. These remain beyond complete explanation. The more we uncover, the deeper the mystery grows. Perhaps the brain is so complex it can never fully know itself, like a book that cannot read its own pages. And maybe that is fitting. The brain gives rise to curiosity, wonder, and the urge to explore, including the mystery of its own existence. As you rest tonight, know that inside you is not just a biological organ, but an unsolved enigma, vast as the cosmos, quietly working, dreaming, and glowing with secrets. Thank you for joining me on this gentle journey through the hidden landscapes of the human brain. We've wandered through its folds and circuits, exploring the strange illusions that shape reality. We've seen how the brain can invent sensations that don't exist, how it can light up with love, adapt after devastating injury, and even keep humming softly in the minutes after the heart grows still. We've discovered its power to replay the past like a film, to imagine futures that have not yet come, and to create entire worlds in the quiet theater of dreams. It is tempting to see the brain as only a control center, a biological machine. But it is more than that. It is the storyteller of your life, the painter of your inner world, the quiet weaver of every memory and feeling you've ever known. In its delicate patterns of electricity and chemistry, whole universes of experience are born. As you drift into sleep, notice how even now your brain is carrying you forward, slowing your breathing, loosening the grip of thought, allowing the weight of the day to fall away. You don't need to guide it. The rhythms of your mind are already leading you into rest, like waves carrying you out into a quiet ocean. If you've enjoyed this journey, I'd be grateful if you gently pressed like, subscribed, or shared a thought in the comments below. It helps others find their way here too, one sleepy soul at a time. And with that, let the day fade quietly behind you, and let your mind drift wherever dreams may take you. Good night.